Yep, thanks. So, hello everyone. I am Parth Shah. I'm working in IBM Linux Technology Center, and I'm working on this Turbo-Sched project since last 8 months, and I have submitted V2 on LKML. So I'll discuss regarding that, and so yeah. So I will start from that. What is the turbo frequency, and why we cannot sustain that frequency? That is really a power budget controlling thing only, but this is like in server side. So and I will talk about that why CFS is not able to handle this, why we are not getting or sustaining turbo frequency for longer time. We are able to reach to turbo frequency, but the problem is how to sustain it for longer duration. And then the TurboSched algorithm and the results. So in multi-core or many-core systems, we have a rated frequency, which we call it as a base frequency or nominal frequency, which we can sustain in all the cores at any time. But then we have a turbo frequencies, and we cannot sustain that frequency for longer duration in all of the cores at a time. That's because that this frequencies burns more power, and we have a power budget fixed in the chip. And since the power budget is fixed, so system will throttle the frequency to the lower frequency in case if we exceed the power budget. So that's what makes us difficult to sustain the turbo frequency. Then how to sustain the frequencies? If we can remain within the power budget, then we can sustain it, and that's how we can use the CPU idle in that case. Since CPU idle helps us in saving power for some of the CPUs, we can put some of the CPUs in idle states for a shorter period of time, and that saved power we can channel it to the busier cores. So that's where the TurboSched policy will come in, that what we want to do is we want to keep maximum possible CPUs idle so that we can channel that saved power to the busier CPUs. So as I said, with CFS, we are able to reach turbo frequency, but we are not able to sustain it for longer duration. That's because CFS does task spreading. It tries to optimize the resource management, and it tries to get more memory from all the cores. So the basic problem is it is doing task spreading, which is, yeah, of course, it has better advantages. It is a performance oriented thing, but the only problem is that it wakes up an idle CPU even in case when it is not required. Like if some noisy task comes in, some operating noise comes in, it wakes up an idle CPU if there is any available. So it is performance oriented, but for TurboSched it is not required. So that's where if we can tune CFS for that purpose, then we can sustain turbo frequency for longer duration. Other thing is CFS is basically per CPU scheduling thing, and it doesn't look at the core concept from power budgeting point of view. So the thing is that we have a frequency domain in such servers is per core basically. So we have this DVFS controlling per core, and that's where when I was trying to make these patches, I was thinking that whether we can use EAS or some kind of other framework by which we can regulate the power budget within the server. But the problem is the frequency domain is per core, or even in some systems we have per 4 cores or per 6 cores. So the frequency domain is not a single CPU, and that's where it's difficult to control the frequency within a chip. But yeah, the idle domain is per core. We can put a core into idle state, and we can save the power per core in that case. So I was talking about that we can put several CPUs into idle. So now what we can do is we can pack task into a busier cores rather than busier CPUs, and we can try to keep a maximum number of possible cores idle. So that's where the task packing comes in. If we can pack the task into fewer number of cores, then we can sustain the turbo frequency. And this is the experimentation I did on IBM Power 9 system, which is a 16-core system. And this chart says that in base or normal scenario, if I'm running a workload which is spreading across whole chipset, then I'm able to sustain 3.3 gigahertz, or it's varying between 3.3 gigahertz and 3.4 gigahertz. But if I offline 2 cores, then I'm able to sustain 3.5. And in similar way, if I offline more cores, then I'm able to sustain 3.8 gigahertz, which is the maximum turbo frequency in this case. So yeah, so this result is basically from user space. I was just hot plugging out few cores, but yeah, this is not possible to do it in production system. This was just experimentation, which shows that yeah, whether we are able to sustain it or not. And this shows that yeah, offlining few cores, we are able to sustain it for longer duration. So if from kernel scheduler, if I offline 6 cores, or if I put 6 core into the idle state, then I can allow other cores, which was like, this was 16 core system, so I can allow 10 cores to be in turbo mode. So it can run in highest frequency, which is 3.8 gigahertz. We cannot, so yeah, as I said, CFS is best for performance oriented workloads. And that's where I come into the classification. We have two classification, which is a CPU intensive, and the other is, let's say, jitters, which is nothing but a noisy workloads. So CPU intensive tasks are CPU bound and memory or cache hungry tasks, and they are performance oriented, and CFS is the best algorithm for it. But for jitter tasks, these are like system daemons or housekeeping tasks, which are some low utilization tasks which are coming in and going out, and they are maybe bursty workloads, shortcoming bursty workloads. And we can pack this kind of task into the busier cores. So that's what, that if we can pack only jitter task into the busier cores which are running CPU intensive tasks, then that will be the best algorithm. And that's why the CFS is not good choice for this kind of tasks. So this is the system that I was using, IBM Power 9 system, which is 16 core system, but the frequency domain for this system is set of 4 cores, and that's why we cannot use any kind of model or framework for the controlling power budget. And yeah, it is 4 SMT system, and the turbo frequency range is 18%. So if you are not able to sustain it, then you are losing out 18% of the performance. And also the workload that I'm using is a synthetic custom-made workload. It has these two kinds of threads or tasks which it can spawn. One is CPU intensive task, the other is jitter. CPU intensive, it does just integer operations in while loop, that's it. And jitter tasks are time integer operation, they are frequency invariant. At whatever frequency you run it, they will do just X amount of operations. And what I saw was that if I run both this kind of task, one intensive task and one jitter task on a single core, then I can see that this intensive task will suffer a 4% regression. So yeah, so we have 18% turbo frequency and 4% regression. So even if you try to pack a task on cores which are running intensive tasks, then also you can get a 14% benefit compared to the CFS. So that's why we want this Turbo-Sched. Other thing is why we cannot dedicate a separate core to just housekeeping tasks. So that's where I did the experiment. I tried to pack tasks in 2 different ways. One is isolating it, other is side-by-side packing. So isolating it is like I dedicated a core for all these jitter tasks, and other tasks like CPU intensive tasks are spreaded using CFS. Whereas in side-by-side packing, I'm putting this jitter task on the cores running this intensive task, on the sibling threads of the cores running intensive task. So this is side-by-side packing, and the result that I saw was that with side-by-side packing, I'm able to see more frequency gain compared to the isolated packing. So this chart says that how much frequency we are able to gain compared to the CFS. So these are all relative numbers. So and x-axis represents that how many number of jitter tasks plus intensive tasks are spawned. So basically number x, or let's say number 6, represents that there are 6 intensive tasks plus 6 jitter tasks. So it will be 2x number of threads. So from this I came to conclusion that there is still a better way by side-by-side packing, and allowing a dedicated core can also give us more frequency, but there is still more opportunity with side-by-side packing thing. Yeah. So then there is this task wake up logic. So in scheduler we have this wake up path and load balancing path, and What we can tweak here is that if we can tweak the task wake up logic, where the jitters are waking up for a momentarily time, and if we can pick those tasks even before the load balancer wakes up, then it will not give much performance regression as well. So consider the scenario given here. Let's say that we have a waking task of which is having 12% utilization, and this chart represents that we have a 2 cores, and this is the utilization of each CPU, and the highest capacity is shown by light green box. And the decision that we have to make here is that when a task is waking up and it's 12%, so let's say we have classified the task as a jitter, then where to pack it, where to place it. So we have a 2 decision to make. One is which core to select, and inside a core which thread to select. So we can select here a core 0 or core 1, and after selecting it, we can go with either of the CPUs in that core. So if there was CFS might go with CPU 5 and 6, but what I want is if we can pack it on the CPU 0 of a core 0, then that won't suffer much performance penalty, but they will get more performance boost because of the turbo frequencies. So TurboSched optimizes for performance per watts counter, and not just for the performance. And the policy that the patch set that I posted out, it uses the first fit core. So what it will try to find is that whether I can fit the task in a core, and it is not exceeding the capacity, then it will try to fit the task inside it. And I am searching across whole die or LLC domain inside a scheduling topology. And I will not use those cores whose utilization is 12.5% or less than that. So in this case, it will not try to wake up on core 1 because of that. So that's this is the task wake up logic in TurboSched. Other thing is how much we should pack the task. That's like a tipping point which decides that okay, we cannot go beyond this limit for task packing, and this limit is decided by core occupation capacity. So the core occupation capacity says that this is the capacity of a core with respect to the capacity of a thread inside a core. So if so what I want is that for SMT4 cores, or the core which are having 4 online CPUs, I want to scale it by 1.5 times the capacity of CPU, and that's why I came up with this formula, which scales the core capacity based on the number of online threads. It scales linearly, but it doesn't go beyond the 2 or 3 value. Like yeah.
Can you remind me what is, like, how many threads do you have on your Power 9 machines? Because there are strange numbers.
4 SMT, so 4 threads.
4 threads.
In a core.
In a core.
In a core, and 16 cores, so total 64 threads.
You don't have 8 threads per core.
No, that was
We
Power
have
8.
like
Okay.
the system I'm using is 4 SMT mode system.
Okay.
But yeah, we have SMT8 as well.
And now SMT8 on Power 9 is a lie.
Yeah, SMT8 on Power 9 is right, but in Power 8 we had.
Okay.
So yeah, so if it was Power 8.
So SMT mode, that variable in the formula there, it has the value of 4.
Yes, correct. For this system it will be 4.
So 1 plus 4 divided by 8. So 1 plus 0.5, right? Okay.
1.5.
And how many cores form an LLC domain?
LLC domain in Power 9 is basically a 2 core.
Okay.
So what I wanted is like if you can go up to die domain, but with architecture it difference here. So yeah, we can either go with die domain or LLC domain. So yeah, in Power 8 we have SMT8. So for that I want to scale it like to 2 times the capacity of a thread. So core capacity will be 2 times the capacity of a CPU 0. So yeah, once the capacity of a core reaches above this, we will not try to pack it, and that's what the tipping point for a core is. And the results. This is what I saw after implementing these patches on Power 9 system. I'm able to see that if I'm spawning around 10 jitter plus 10 intensive CPU intensive tasks, then compared to the CFS, I am obtaining around 16% more frequency benefit. And translating it into the number of operations per second that a workload was doing, that will be like 12% more compared to what the CFS was providing me. So this is the same chart which shows the percentage of frequency benefit compared to the CFS, and the number of WOF tasks or the workload optimized frequency tasks, which says that what are the number of jitter tasks plus number of CPU intensive tasks. And similarly, this represents that number of operations per second which I gained compared to the CFS. So it's a delta in terms of percentage. Yeah. Power, no. But yeah, like power budget is fixed, so I didn't measure power, but yeah, I wanted to calculate the performance per watts. Yeah, that's future.
Because you said, sorry, you said you're optimizing for performance per watt, right?
I'm optimizing for performance per watt, but
so how many watt are you?
He doesn't have the number.
Sorry?
He doesn't have the number.
I doesn't have numbers.
I don't understand the watt performance per watt claim, but when the whole point of Turbo is to use unused watts.
Yes.
So like, why wouldn't it be the same watts?
Yeah, it should be the same watts for a chipset if you consider it for the whole system.
I mean, it might not be, but I'm not saying it's exact. I'm just saying I don't quite understand the base claim.
Yeah.
But if the watt is the same and you increase the performance, you can
But it's not the same, because if you're in Turbo, you're in higher watts.
You can use the unused watt, you were saying, right?
Whether you wake up another core or you go into Turbo,
Yeah.
you're using watts either way.
Didn't you say that the goal of Turbo is to use unused watt?
Watts that would be used by running that other core.
Right, exactly.
So using those watts whether you run the core or whether you run in Turbo.
Yeah, and that still gives like a benefit in terms of performance per watt. So he's getting some benefits in performance, and well, you can argue that probably is more than 12% the increase in watt.
But I think Paul is saying that those watts will be utilized by the other core to do useful work.
You have more capacity with the extra core.
That's not true.
Not necessarily, that's not
Not
true.
necessarily, because
Oh,
if
so
you are
this
not-
is
if
interesting.
you are not in a turbo range, you are not using the full power budget of the chip. That's by definition.
But yeah, but we were throttling, so I saw that. Yeah.
No, by definition, so the definition of turbo is
Yeah.
that it is not sustainable because of the power budget.
Yeah, correct.
It can be sustainable.
I mean, if you have
yes.
enough components on the system,
In general, it isn't.
I mean, it can be sustainable. It's just it's your TDP.
Yeah.
If you can dissipate 250 watts, then you're sustainable at 240.
But then you may also get, there are also temperature limit.
That's the
Very-
TDP. That's what I just said.
Yeah, yes, okay. So they, all right, so let's not go into too much details. But anyway, the point is that if you are below the turbo range, you are not using the full power budget.
Okay.
Yeah, but okay, this is, it will be easily, I mean, if you can get a power meter and attach to the machine and get a number.
This is trading latency for ops for one task. Your ops per second integral is not increasing, but your ops per second looking at an individual task may be, because you've traded latency for your quote jitter tasks.
Exactly, you're just prioritizing one task and just giving everything to it rather than spread it across.
Yes.
And you're still living within your maximum power budget. So your budget might have increased, but you are actually letting one task run full throttle for as long as it can run.
That's why I was saying the percent has increased, because if you look at the curves, there is at least, I don't know at the Power 9 curves, but for all the Intel curves, there is no point on the curve for which Turbo is more net capacity than one more CPU plus the turbo limit of that point.
So Parth, you shouldn't say you're optimizing for performance per watt. You should probably say what Paul just.
You're optimizing for single thread performance. of the
Yeah, you're
sensor.
trading.
That's what you're doing.
Yeah, it's more correct and clearer for everybody to understand.
Yeah. Thanks. Yeah, I'll rectify that. So yeah, we got performance, and that's what was motivating for me. And what I wanted next is So there is this thing called jitter classification. So can we use any kind of mechanism to classify the jitter? The one thing that I used right now is from user space using C group, you can classify that, okay, this is jitter, try to pack it. I'm hoping that we can use something like uclamp, or maybe we can extend it, or maybe we can come up with some other approach. Yeah, I'm just eager to extend uclamp because it anyway does clamping thing. So
Well, I think the only thing they share is the idea that you tag task with properties, which is like, but it can be used. I mean, you can't easily focus it on defining properties in terms of utilization that we expect for a task. But what you are
so
you're looking is like another kind of attribute, which is interesting.
but so yeah, currently what I did is that in uclamp, if the max clamping is falling into the first bucket or the zeroth bucket, whatever,
Yeah.
then we say that, okay, it is maybe jitter.
Yeah.
And yeah, so that's
One thing that we still don't have in uclamp is actually the usage of uclamp to bias task placement. That's one of the things that we want to work like as a second step once the core bits are kind of agree and we are okay. So in that domain, when we enter that space, probably we can try to see.
But for us, it's only in the energy-aware path, right?
Is in the is in the wake up part, right?
But for
we
energy
don't have any proposal right now on Kevin on how to use uclamp to bias the wake up part task.
It still feels like what you actually care about is the latency tolerance of the task.
Yeah.
It's not that it's a jitter task, it's that it's a task that can wait to run.
Right.
Because you might have a task that looks like a jitter task that has a very low latency tolerance because they want, like, it's your UI thread, right? That's going to look exactly like jitter but have no tolerance.
Yes.
Rather than, like, it seems like the specification you want is actually more like,
Skid batch or something.
not sked batch, but it's like,
Skid idle or something.
or
It's the opposite.
even skid idle doesn't quite do it because that doesn't tell you like
the opposite of
when
it.
it's like an inburst deadline. But I can wait this long if I get good if like a convenient CPU becomes available. Otherwise, do run on another core.
Yeah. But the good point for me is that we have this need to tag tasks with properties that can be used and
But
somehow from the ship.
I'm still arguing that property to me seems like latency tolerance, not just
Yeah.
because that's not a heuristic.
So basically, is that in another property to read the uclamp interface? Because with uclamp, you only have a utilization, right? In this case, I'm not sure how you can use that to implement the policy. Right?
And what about this soft affinity stuff from yesterday? If you know that your task you want to run.
So I was actually just saying to Peter, like, soft affinity would give you probably the same benchmark result if you said always, like, you shouldn't implement it this way, but if you said always wake me up on the CPU 1, but don't continue on CPU 1, that means like if you wake up and you hang around long enough there for the load balance to move you to an idle CPU, otherwise you'll queue on CPU 1 for a little bit and run there naturally. It's the same kind of idea, but the formalization of that is how long can I wait, right? Like what's the latency tolerance that I'll wait for an opportune CPU versus okay that in-burst deadline's expired, run me somewhere. We have stuff like that on the wake up path that's not really ever used for some of the daemons. I forget what the stuff I ended forever ago.
Latency too?
No. There's some like for some of the daemons like it's a latency tolerance to how long to try and align the wake up. Yeah. You know what I'm thinking of. But I know. But it was never really properly implemented. It was a hack on top of it.
Can you just describe a little bit better?
Timer slack, yeah. Timer slack is sort of like this idea, but not like a unified thing.
Timer slack.
Yeah.
So there is a user space approach that is similar to that in fact because there is also the idea is to have a CPU set which is growing depending on how many processes are run.
Okay.
And so if you have a queue, then it's just one CPU in that set. And then it only grows when the CPU is entirely utilized.
Okay.
And then it has the next one, and then you can put tasks on it within the set. And then when the second CPU is fully utilized, then the third one is added to the set by a user space daemon. And
But in this case, you should keep count of how many non-jitter tasks you have in a group and extend the group in order to have possibly one non-jitter task.
So my question would be, how much better this is with respect to the user space solution I mentioned.
Yeah, I'll see that. I'll try to do experimentation towards that as well. Okay. So yeah. Okay, I'm happy to extend this jitter classification with any other approach. The other thing is, like, can we come up with some other framework, like some EAS? Of course, we have challenges in EAS, like the requested frequency and the obtained frequency cannot be same, so I cannot guarantee the frequency from EAS model. And of course, for servers, it won't work because complexity is too much. But yeah, if there is any other model, then that will be better. But yeah, and this is the LKML page or the RFC that I have posted, so happy to take your comments on that as well. Thanks. And the legal student. Yeah.